Hello everyone. Welcome to our new session of fluid mechanics and hydraulic machines. Today we are going to start our new topic, that is Hagen-Poiseuille formula, and which is used for the flow of viscous fluid which is flowing through the circular pipe. Okay, so today in this session we will cover about the viscous fluid that is flowing through the circular pipe, and we will find over there the shear stress distribution and the velocity distribution with the drop of pressure throughout the cross section of pipe at a section 1 and at a section 2. So at the end of the derivation we will find out the pressure drop as well as the frictional loss as per the viscous fluid in the circular pipe. So let's start our today's session, that is the flow of viscous fluid through the circular pipe. Okay, so let's start our session. From the starting of the session, here we are having some of the previous formula that is basically based on the Reynolds number. So if we talk about our previous session, in that session we'll cover about Reynolds experiment. So at the output of that experiment, we'll have the laminar flow, the transitional flow, and the turbulent flow. It means that when you are having a flow which are having a Reynolds number less than 2000, that type of flow is called the laminar flow. When you are having the flowing fluid which is having a Reynolds number in between 2000 to 4000, and that type of flow is called transition flow. So whenever you are having a Reynolds number is greater than 2000, greater than 4000, and that type of flow is called turbulent flow. So that was all about our previous session. And in this session, in this Hagen-Poiseuille formula, the velocity distribution across the session will find out the ratio of maximum velocity to the average velocity. Okay, first of all we will find the velocity distribution. After that we will find the ratio of maximum velocity to the average velocity in the circular pipe, and also we will find out the shear stress distribution and the velocity distribution, and at the end of this session we will find out the drop of pressure at the cross section of pipe for the given length of pipe. So in the circular pipe, let us assume that the viscous fluid or the laminar flow is flowing. It means that it has a Reynolds number less than 2000. So experimentally and theoretically we will derive that the Reynolds number Re that equals to a rho Vd by mu. Okay, rho Vd by mu, that is the expression or the formula for the Reynolds number, where the rho, that is the density of flowing fluid which is flowing through the pipe, V, capital V, that is the average velocity of fluid, D, which is your capital D, diameter of pipe, and the mu, that is the viscosity of fluid. So it gives you the Reynolds number. Okay, so we are having total three types of formula and the three types of fluid. When your Reynolds number is less than 2000, whenever your Reynolds number is in between 2000 to 4000, and when your Reynolds number Re is greater than 4000. So in the first case, when your Reynolds number is less than 2000, that is laminar flow. When your Reynolds number is 2000 to 4000, Reynolds number is in between 2000 to 4000, so this type of flow is called transitional flow. And when your Reynolds number is greater than 4000, this type of flow is called turbulent flow. So this theory which is covered in the previous session in detail with the experimental view. So let's start our Hagen-Poiseuille formula, and that is, let's consider a horizontal pipe. In this figure you can see that one horizontal pipe, and the fluid flow is flowing from the left side to the right side in this pipe section. In this pipe, we are considering a small fluid element which is a radius of r. You can see that over here. It has, this is our small fluid element which is a cross-sectional, circular cross-sectional fluid element. In the side view you can see over here. It has a radius of r, and the thickness of this circular fluid element is dr. Okay. So the total radius of this fluid element, that is r plus dr, from this at the center of pipe r plus this dr, that is the total radius of this small fluid element, and delta x is the length of a fluid element. Okay, so ABCD, which is the small fluid element, which are having a radius of r, and the thickness of this fluid elementary ring, which is dr, the length of this fluid element, that is in x direction, which is delta x. So let us now considering the pressure intensity which is acting at a side AB, that equals to P, because our fluid is flowing from the left to the right side. So the pressure is exerting on the side of AB, that is P, which is exert on this AB side. So that the intensity of pressure in this side CD, that is the P plus del P upon del X into delta X, it means that P plus del P upon del X change in a pressure with respect to this distance delta X into dx. So these all are the forces which is acting on this side. So here it is the forces. The first force, that is force equals to pressure P into area of this elementary ring, that is pi r square. Okay, area of this elementary ring, that is pi r square. So the force that equals to pressure into area which is applied on the face AB. Likewise, second force we are having, that is applied on this side CD, that is P plus del P upon del X into delta X. It means that the pressure intensity changes in the direction of X. So mathematically we can write that P plus del P upon del X into delta X. So here it is the value of pressure into the area, that is pi r square, which is applied on the side CD. Okay, and the third force, which is the shear force, that is applied in between the element of this pipe and the pipe surface, inner pipe surface of this cross section. So that the shear force in between these two surfaces, surface this and this, that is tau into 2 pi r, that is the peripheral area of this circular cross section, tau, that is the shear stress. We are talking about the force, we are going to find out force. So the force that equals to stress into area, area is 2 pi r into dx, that is the length of this cylindrical small element. Okay, so here it is the stress into area. So this is our shear force. Okay, this F is the shear force. Okay, so total three types of force which is acting on this circular pipe. First is P into pi r square. Second force is P plus del P upon del X into delta X. That is the pressure force, or pressure into the area is pi r square. Third force is shear stress into area. So here it is the no acceleration in this flowing fluid, and the summation of all the forces in the flow direction, that will be a 0. So let's do a summation of all the forces. So the first force, that is P r square. Second force, that is applied the opposite to the first force, that is why it is over here is the negative sign, and this one is our second force which is applied on the CD side. And again the third force, that is again the opposite direction to the fluid flowing. So the negative of third force, that is tau into 2 pi r into delta x, that is equals to 0. So after opening this bracket and multiplying this pi r square with the p pi r square and del p upon del x into delta x into pi r square. So after the multiplication, the cancel out, this term will be cancel out p into pi r square. So the remainings are a negative of del p upon del x delta x into pi r square, this is our first term, minus tau into 2 pi r into delta x, that will be equals to 0. Okay. In the next step, this delta x and this delta x, also this pi r with this pi and r square will be cancelled out, so that the remaining terms are minus del p upon del x into this r minus 2 into tau. So that del P upon del x into r minus 2 into tau. So we can write that tau that equals to minus del P upon del x r by 2. So here it is the one equation, that is the value for the shear stress, that is del P upon del x r upon 2. Okay. So the shear stress tau across the section which is varies with the r that is the radius, whenever del P upon del x across the section is constant. So from this equation we can conclude that when your del P upon del x, this del P upon del x across the cross section is constant, at that time your tau shear stress is directly proportional to the radius of pipe. Okay. So we can say that the shear stress distribution is somewhat like this, wherever the shear stress is 0 at the center of pipe and shear stress is increases whenever you are increases the radius of pipe. So here it is the shear stress distribution somewhat like this, okay, in the pipe cross section. I hope you can understanding this shear stress distribution. When the R is 0, which is at the center of pipe, your radius of small elementary cross section is 0, at that time your shear stress will be 0. So whenever you are going towards the peripheral side of the cross section pipe, at that time your shear stress is also increases with the increases of radius. Okay. So we can conclude that the tau is increases with the radius of pipe. So first thing we'll find out, that is the velocity distribution. To obtain this velocity distribution across the cross section, the value of shear stress tau is somewhat like this, and this equation is known as the Newtonian equation. If you are remember our first chapter, at that time we have studied the Newtonian equation or the Newton's law of viscosity. The Newton's law of viscosity is telling that the shear stress, Newton's law of viscosity is shear stress is directly proportional to the rate of shear strength, that is du upon dy. In this equation, if you are going to replacing this proportionality sign by equals to mu, this proportionality sign is replaced by this equals to mu. So we can write that tau that equals to mu upon du mu into du upon dy. So this mu, that is the terms for viscosity. Okay. So here it is the same equation, that is tau equals to mu into du upon dy. This equation is known as Newton's law of viscosity. So let us find out the velocity distribution from this basic equation. As we know that the relation tau that equals to mu du upon dy, where the y is measured from the pipe wall vertically. Okay, here it is the pipe wall, here it is the elementary area. So y is measured at the pipe wall from the vertical direction, so that we can write that y equals to capital R minus small r and dy equals to minus dr. So by putting these two values in the above equation, we can write that tau that equals to mu du upon minus dr, that equals to minus mu du upon dr. So let's substitute this value in this previous equation. In this previous equation, our equation number 1, let's substitute this value over here, tau, so that we can write that this tau equals to like this minus mu du upon dr. So we can write that tau equals to minus mu du upon dr, and the remaining terms are equals to minus del p upon del x into r by 2. So let's simplify this term. Over here left side du upon dr, that equals to 1 upon 2 mu del p upon del x into r. And let's integrate this above equation with respect to r to get the whole pipe, so that we can write that after integrating this equation with respect to r, this du upon dr, that is u, that equals to, now in this case this r, integrating this r, so it will be your r square by 2. So by 2 into this 2, that will be your 4 mu dp upon del p upon del x into r square plus constant. So we need to find out the value of this constant, where the c, that is our constant integration, and its value is obtained by applying the boundary condition. We need to apply boundary condition when your small r that equals to capital R, at that time your u that is 0. What does it means? When your small r, in this equation, in this diagram, we can see that small r is nothing but the radius of this small elementary area, and the capital R is the radius of this pipe. So when this small r that equals to capital R, it means at the end of this pipe, at that time your velocity equals to 0. Your velocity is equals to 0. In this case, you can see that at this point your velocity is 0 because of friction in between the flowing fluid and the inner surface of the pipe, so that whenever small r that equals to capital R, at that time your velocity that equals to 0. So let's put out the value of u that equals to 0 in the previous equation. So over here u that is 0 equals to 1 upon 4 mu del p upon del x into r square plus c. So take out this plus c in the one side, and remaining terms will be in the right side. So it will be your negative of 1 upon 4 mu del p upon del x into r square. So by putting these value of c in our previous equation number 2, in this equation number 2, let's put this value so that we can write that u that equals to, this was our previous equation, 1 upon 4 mu del p upon del x r square plus c, but this c is replaced by this equation minus 1 upon 4 mu del p upon del x into r square, into r square. So take out common this 1 upon 4 mu del p upon del x, 1 upon 4 mu del p upon del x. So the remaining terms are r square minus r square. So this is our remaining term, and the u that is the velocity. So this one is our new equation number 3, where the value of mu del p upon del x and the r, these terms are the constant, so that we can see that the velocity u is varies with the square of r. Velocity u is varies with the square of r. So in this equation is known as the parabola or the parabolic equation. So you can see that in this diagram, this velocity u is varies with the square of r. So it is somewhat like parabola. So it is called that the parabolic equation. It means that at the center of pipe we can have a maximum velocity, and at the end of pipe there is a 0. U is 0 at the end of pipe, and u is maximum at the center of pipe, where the r is 0, at that time u is maximum. Okay, so we can conclude that like this. So let us find out the maximum velocity. That is the maximum velocity and average velocity. Next, second term that we need to find, the velocity is maximum, as we know that when your small r is 0. It means that in this diagram you can see that when this r is 0 in this center line, at that time your velocity is 0. Okay, you can see that in this equation. Okay, so when your r is 0, in that equation umax is obtained. So we can obtain from this previous equation, whenever you are taking this r is equation, so remaining terms is known as the maximum velocity. So here it is the umax that equals to 1 upon 4 mu del p upon del x r square. The second thing we need to find, that is the average velocity. So this average velocity we will find out from the discharge of the pipe. So let us find out first of all discharge from the pipe, and from that discharge we will find out the average velocity. So the average velocity u is obtained by the dividing the discharge from the fluid cross section area, and the cross section area is pi r square. The discharge is known as dq, that is the velocity into area, q that is the velocity at radius of r and the area of ring element. So velocity at the radius of r, that is u, and the area of ring element, that is 2 pi r into dr. Over here you can see that this is your 2 pi r and the thickness of this ring element, that is dr. So the velocity, or sorry, the area of the ring element, that is 2 pi r into dr. Now put the value of u velocity in this equation. So that is equals to minus 1 upon 4 mu del p upon del x r square minus r square from this equation. That is equation number 3. So this equation is u and the remaining are the area of the ring element, that is 2 pi r into dr. Now let us integrating to find out the whole discharge from the whole pipe, total discharge. So let us integrate from 0 to capital R, integrating this dq 0 to capital R. So minus 1 upon 4 mu del p upon del x r square minus r square into 2 pi r dr. The constant terms are outside from this integrating sign and the remainings are r square minus r square into r dr. So into r dr, and multiplying this r with this inner bracket, so we can have this equation. And from that equation, by integrating the r square, that is r square by 2, r square by 2, and over here that was the r in this equation. Over here that was r cube. So that r cube will be in the form of r raised to 4 by 4, and this is our upper limits and lower limits. So by putting upper limits and lower limits, we are having this equation, and finally after the simplifying that equation, we are having the discharge, that is pi divided by 8 mu into bracket del p upon del x r raised to 4. So over here your average velocity, that is discharge upon area, that is from this equation, discharge that equals to area into velocity, so that the velocity that equals to discharge upon area. So here it is the equation, that is velocity that equals to discharge upon area. Okay, so this one is your discharge q. So by putting this value of q, pi upon 8 mu into bracket minus del p upon del x into r raised to 4 divided by pi r square. So the mu bar, that is average velocity, 1 upon 8 mu minus del p upon del x into r square. So by dividing, what we are going to find? We are going to find the ratio of maximum velocity to the average velocity. So the ratio of maximum velocity to the average velocity is somewhat like this, and that equals to 2. The ratio of maximum velocity to the average velocity, that equals to 2. And the third thing, that is to find out drop of velocity across the length of pipe from the section 1 and section 2, where the total length of pipe, that is x2, and the starting of cross section 1, that is x1. So the length, that equals to x2 minus x1, that is your L. So from the average velocity equation, that is 1 upon 8 mu minus del p upon del x into r square, or we can write that this same equation in the form of pressure drop, that is del p upon del x, that equals to this 8 mu is going upside, so 8 mu u bar divided by this r square. Okay, so let us integrate this term with respect to x, that is x direction horizontally. So by integrating with respect to this x, we are having 1 to 2. We are integrating from this cross section 1 to 2 del p, that equals to 1 to 2 8 mu u bar r square. Okay, so this dp is p1 minus p2 8 mu u bar divided by r square, and by putting the upper limits and lower limit 1 and 2, we are having this x1 and x2, x1 minus x2. So this x1 minus x2, that equals to L. From this diagram we can see that. So 8 mu u bar r square into L. We are replacing this x2 minus x1 by L. and this R is nothing but the d by 2. R is nothing but d by 2. So P1 minus P2, P1 minus P2 that equals to 32 mu U bar L divided by d square, where P1 minus P2 that is the drop of pressure across the length of pipe. But as we know that the pressure head loss or the loss of pressure head, that is P upon rho g or P1 minus P2 upon rho g. This one is our loss of pressure head. So we can write that P1 minus P2 upon rho g that equals to 32 mu U bar L divided by d square. So we are dividing this equation by rho g. This previous equation, we are dividing this equation by rho g over here and rho g over here. So that we can write that equation P1 minus P2 upon rho g equals to 32 mu U bar L rho g d square. So this equation of pressure, loss of pressure head, HF, loss of pressure head, this equation is known as Hagen-Poiseuille formula, and this equation is most IMP equation of this chapter. Okay, so you need to remember this equation for the examination and also for the example point of view. So in a very next lecture we'll solve the example based on this head loss due to the pressure head, and the equation of head loss due to pressure head, that is 32 mu U bar L divided by rho g d square. So in this Hagen-Poiseuille formula, this question is about 7 marks of question, and you need to write down this whole derivation in the 7 marks. Okay, you need to